Hopefully we've now built an intuitive understanding of what generators mean in classical mechanics. Now it's time to have a look at the quantum picture. Now if I scroll back to the classical picture, let's relate these terminology to quantum mechanics. Now, a state in the classical picture was an element of the phase space, but in quantum mechanics, a state is an element of the Hilbert space. An observable in the classical picture was a function that mapped our phase space to a real number. But in quantum mechanics, observables are Hermitian operators that map a subspace of the Hilbert space to the Hilbert space. These have real eigenvalues, and that's what we observe. Now, the next important question to ask is, how do we construct this observable? Before we answer that question, let's make sure that our basics are clear. Our operator that represents an observable is Hermitian on the subspace dA. Bit of technicality, if an operator is self-adjoint, it implies that it is symmetric, and we call such operators Hermitian in quantum mechanics. Being self-adjoint means that the operator is equal to its conjugate transpose. So in quantum mechanics, being Hermitian means being symmetric and self-adjoint. Essentially, if we find these self-adjoint operators, we have constructed our observable. Now I'm going to introduce a very powerful theorem called the Stone's theorem, which states that let U be a unitary Albinian one-parameter group that is strongly continuous and whose group law, if you compose two elements with parameter t and s, the resulting element will have the parameter t plus s, and an element with parameter 0 is the identity on the Hilbert space. Then, the generator of this group, A maps some subspace of Hilbert space to H, is self-adjoint on its domain. Woohoo! Now we've found a way to obtain our observables. We just need to construct these unitary Albinian one-parameter groups with certain group laws, and we'll be able to get our generator. Then the generator will be our observable. We can actually recover the unitary operations in the group using the generator. So you've seen some of these things in our lectures. Group is a set of transforms. Being unitary just means that if I have a transform U, then the U conjugate transpose times U will just be the identity on the Hilbert space. Being Albinian means that two transforms from my group commute. Being one parameter means that every transform in my group can be labeled with a single parameter. Being Albinian one parameter produces this condition. This just tells us that having a transform with parameter 0 does not change my state. The final piece, being strongly continuous, means that for all states in the Hilbert space, if my parameter t approaches t0, then the resulting transformation will be given by the parameter t0. Alright, so the next obvious question is, what is the generator of a unitary abelian one-parameter group? The answer is actually quite simple. Now I'm going to use the operator notation, so I'm going to give these hats. And so let's say that our generator acts on some state psi in the Hilbert space. Then this will be given by limit as small parameter epsilon tends to 0, and the difference between the unitary operator with the parameter epsilon acting on our state and the state itself divided by the small parameter. The resulting state can be described by our generator acting on that state. Now let's take a moment to analyze this. Like in the classical case, we had generators creating these flows in the phase space that translated our states. Note that we've picked a very specific example here of a group that is unitary abelian and one parameter, but this may not be true in general. For the scope of this video, we can say that generators in quantum mechanics generate groups of transformations that translate or rotate the state in Hilbert space. Here, we can think of groups as what creates flow in the Hilbert space using the set of its transformations. Now we're going to look at a few concrete examples that's going to clear up everything from the lectures. I'm going to call these groups UAO PG. So to start with, let's have a look at the spatial translation operator. Now nothing on this slide is new, we've seen this before in the lectures. If you write our wave function in the position basis, our spatial translation operator t, parameterized by x0, takes our state x to a state x plus x0. Now here I've shown the action of our spatial translation operator on the state. So in the lectures, we've shown that this is unitary, and we can see that it takes a single parameter. So if I were to form a group G with set of translation operators, Now we can easily show that this is abelian because the order in which we perform spatial translations do not matter. Now because position is a continuous variable and t is defined everywhere, we can show that this group is also strongly continuous. That means that we have constructed a unitary abelian one parameter group. So conveniently, we can now use Stone's theorem that our spatial translation operator can be written in this form and that the generator can be found using this equation. So in the generator, therefore, we see that the momentum operator is a generator for spatial translations operator. And that's similar to the result we got in classical mechanics. So indeed, in general, momentum can be defined as a generator of spatial translations. Now these translations are in the relevant spaces. So in case of classical, we had translation in the phase space. Quantum, we have translations in the Hilbert space. In lectures, we started with this form from Stone's theorem and guessed that the generator would be the momentum operator based on our classical knowledge. But in fact, it's actually possible to calculate it now that we know about these groups. Let's consider an example of a free particle. Now we know that our state will be invariant under spatial translations. That means we have a symmetry. This symmetry will not change in time, thus it's time independent. And as x is a continuous variable and t is defined everywhere, the symmetry is also continuous. Now Noether's theorem states that the generator of a group with elements that have time-independent continuous symmetry will represent a conserved quantity. Therefore, in this case, from what we've seen before, the momentum observable will be conserved. Another example could be a group of unitary time evolution operators. This group is generated by the Hamiltonian, and thus if we have a system that is invariant in time, the total energy will be conserved. Now, if you remember, in the lectures, we started talking about transforms and generators while discussing symmetries and conservation laws. Indeed, because we only considered time-independent continuous symmetries, we could apply Stone's theorem and obtain the generators. I hope this video was useful, at least in terms of clarifying why we introduced group theory, what's the significance of Stone's theorem, what do generators intuitively mean, and when do they represent a conserved quantity.